Hello, and welcome back to the next video of our bite-sized integral calculus series. So in this video, we'll be talking about area approximations and how you can relate the concepts of area approximation in order to calculate the integral of a function or a curve. So before I start this video, I would also mention that in order to get a good grasp of the concept that we'll be covering in this video, I would highly suggest if you can watch those previous videos in the playlist, because watching those videos will give you a better idea about what we'll be doing in this video and get a better grasp on the concept that we'll be dealing with in this video. So I'll start this video and we'll talk about area approximations and the motivation behind why we want to do area approximations instead of calculating the actual area under the curve. So we talked about this in the previous videos as well, that if you want to integrate a function or a curve which is represented by, for example, y equals fx, you just have to basically calculate the area under the curve or the area enclosed under the curve bounded by those intervals that you're calculating the area from. So in this case, if you want to calculate the integral of y equals fx, you basically have to calculate the area under the curve which is enclosed between these two intervals a and b. And the answer to the area enclosed under this curve will basically give you the integration of that curve. But if I want to calculate the area under the curve of more and more complex functions, this process of calculating the area under the curve does not seem that simple, right? So that is why area approximations come in handy, and this also serves as a motivation for calculating the actual area under the curve as well. And we'll talk about this in the later half of the video as well. So we'll start with some basic examples which will sort of motivate us to use some other definition of area under the curve or use some approximations that we can use to calculate the area under the curve for more and more complex functions. For example, in this case, as you can see on the left hand side of the screen, you have y equals x square. And if I want to calculate the area enclosed by the curve y equals x square from x equals 0 to x equals 1, which is this interval, I have to basically calculate the area under the curve of this. But you realize one more thing, that it's not easy to calculate the exact area under the curve or the exact area enclosed by this region from 0 to 1, because it's not calculating the area of a familiar shape that I know. It's not a right angle triangle either, that I can just use half times base into height in order to calculate the area. So that is why I'll have to come up with a different way, or a way in order to approximate the area under the curve of this function. So even if I'm not able to calculate the actual or the exact area under the curve, I'll lead myself to a way in order to calculate an answer which best approximates the actual answer. And we can take one more example as well in order to confirm the need of area approximations in order to calculate the area under the curve. So the second function that you see on the right hand side of the screen is y equals e to the power x, and you'll realize the same thing in this case as well. It's not easy to calculate the area under the curve or the area enclosed by this region by taking the area of some similar shapes that I know, for example rectangles, triangles. I just can't use those area of the familiar shapes that I know in order to calculate the actual area under the curve of e to the power x, right? And that is why I need a way in order to calculate, if not the actual, but the answer that closely resembles the actual area of the function that I'm calculating the area under the curve for. So we'll start with the simpler approach that we can do in order to calculate the approximated area under the curve of a complex function. In this example, we'll take y equals e to the power x and we'll build our intuition of area approximations on this function only. So as you can see on the screen as well, you have the graph of y equals e to the power x, and I'll use this fact that it's easier for me to calculate the area of rectangles. So what I'll do in this case, in order to approximate the area under the curve of e to the power x in this case, that we are taking from the interval x equals 0 to x equals 1, I'll just divide the interval into equal parts. In this case, I'll divide the interval from 0 to 1 in 4 equal parts, so that each part has a width of 1/4. And after I have divided my interval into 4 equal parts, what I'll do is I'll take individual rectangles and add those areas of the individual rectangles in order to approximate the actual area under the curve of e to the power x in this case. So what I'll do is, I either have two options. I either have an option to take the smaller rectangle or the option to take the bigger rectangle. Whatever approach I choose, it will either overestimate or either underestimate the actual area under the curve, that we'll see in the next page as well. So what I'll do is I'll basically construct these rectangles and add the area of these individual rectangles in order to calculate or approximate the area under the curve of e to the power x in this case. So the same thing again, I have two approaches. I can either take the smaller rectangles and I can add those areas of the smaller rectangles, each of width 1/4, and approximate the area under the curve of e to the power x, or on the other hand, I can take those larger rectangles, the taller rectangles, and I can just add those areas of individual rectangles in order to approximate the area under the curve of e to the power x in this case. And we also realize one more thing, that if we follow the approach which is given on the left hand side, we are always neglecting some area which should be included in the actual area under the curve. So since in this case I'm neglecting some area which should be included in the actual area, I'm basically underestimating the actual area represented by e to the power x in this case. On the other hand side, you see that I'm always taking some additional area which shouldn't be included in the actual area of e to the power x. So that is why in this case I am overestimating the actual area represented by e to the power x bounded by 0 to 1 interval. And this can also be confirmed with the actual answer that we have for area under the curve bounded by x equals 0 to x equals 1, that the actual answer is 1.718. And if I followed the left hand side approach, I got 1.51, which is an underestimate, and on the right hand side I got 1.9420, which is an overestimate to the actual area that we have on the screen. But no matter if it's an underestimate or an overestimate, it just makes my calculation so much simpler, right? I just have to divide my interval or the area into those individual rectangles, and I just have to sum up those areas of the individual rectangles in order to approximate the actual area. So that is basically the motivation behind calculating the area approximations under the curve, calculating the area approximations of complex functions that we have. And we can also see that from the area approximations that we did so far, even if it was an underestimate or an overestimate, they both very closely resembled the actual area with some minor errors, but we also see that the final answer was very close to the actual answer that we needed. So now let's find a way in order to further improve the answers or the approximation that I've gotten so far. And we can see one more thing as well, that in this case, when we were approximating the area of e to the power x, we took rectangles of width 1/4. What if we make those widths of the individual rectangles even shorter? What if we take individual rectangles of width 1/8 instead of 1/4? So this seems like another way in which we can improve our answer, and that indeed works as well. So the answer that you see, the answer that we want is 1.718, and we used two different approaches again. We took the individual rectangles of width 1/4, which gave us the answer approximation to be 1.512. But if we took rectangles, those individual rectangles of width 1/8, my area approximation came out to be 1.6131, which is an improvement to the previous answer and which also closely relates to the actual answer that I need. And that is basically all the motivation behind integration or calculating the area under the curve, the actual area under the curve of a complex function. I just have to make the widths of my individual rectangles smaller and smaller so that they nearly approximate or become equal to the actual area of the function. Continuing on the example that we did so far, we took individual rectangles of width 1/4 and width 1/8. I would highly suggest you to try with width 1/16 or width 1/32, and you'll realize with your calculations that when you'll keep on taking those smaller and smaller widths, your final answer would become very close to the actual answer that you need for the area under the curve in this case. And that is all we do in integration as well. In order to calculate the actual area under the curve, we just take those individual rectangles of width 1 by n, where n approaches to infinity, and if n approaches to infinity, my widths get smaller and smaller and they become infinitesimally small. And by taking those individual rectangles of infinitesimally small widths, I'm basically taking those thin strips and calculating the area of individual thin strip and summing them up in order to calculate the actual area under the curve. And that is basically what the motivation behind integration is and how we calculate the actual areas under the curve. In the next video, we'll cover this approach in more detail and we'll calculate the actual area under the curve of e to the power x bounded by x equals 0 to x equals 1 by using all the fundamentals that we learned in this video. So stay tuned for further updates. Please follow the channel if you want to get notified about the other videos. Thank you so much for watching. Bye bye.